Maybe we'll get them there. Hi, good morning, everyone. We're going to get started on our first wastewater stream session of our day 2 at the conference. This morning, our first talk is with Soyean Kim, and she is going to talk about genomic wastewater surveillance in smart cities. Soyean works as a product lead at the Center for Infectious Disease, Genomics, and One Health. It's CIDGOH at Simon Fraser University. CIDGOH focuses on infectious disease management through a One Health lens, a multi-sectoral approach involving human and animal health, leveraging advanced computational approaches and innovative knowledge engineering. As a data analytics leader, Soyean has over 18 years of experience working in multiple domains, including consulting, private utility, public health, and government and nonprofit organizations. Soyean is a certified cloud professional and an accredited statistician. Most recently, Soyean worked as a director of digital products at Providence Healthcare. The team focused on leveraging technology solutions to support hospital operations in addition to supporting Canada's digital technology supercluster to develop novel and innovative digital health applications. Soyean works as a member of the United Nations Privacy Enhancing Technology Lab, the UN PET Lab, advocating for sound data stewardship, secure data sharing, and the use of emerging privacy-enhancing technologies. Soyean also served as the chair of the accreditation committee at the Statistical Society of Canada and the United Nations Global Platform, the UN's initiative to increase big data capacity for member states' national statistical systems. Please join me in welcoming Soyean this morning.
Thank you, Chris, for a very generous intro, and thank you for trying hard to pronounce such a long name. The organizations I work for, that's the CIDGA for short, so Center for Infectious Disease, Genomics, and One Health. So that's quite mouthful, but you got it right. So thanks for the chance to interact today, and I'm excited to be here. When I got the invite to speak today at the EOPC, I had a couple of goals in mind. So the first one was that genomic is, especially pathogen genomics, is such a complex topic, but it's going to take more than scientists and specialists to really make a broad impact and operationalize genomics technology and into everyday operations. So for me, it's such a learning experience, and I'm excited to be here to have this opportunity to interact with environmental operators. So I'm stepping outside of my own bubble here a little bit. So thanks for the opportunity. Second one is I like to create a bit of an awareness of this approach called One Health. So One Health, simply put, is this connection between our health and the organism, plants, and animals that surround us. So how we impact them and how they impact us. So in the healthcare, for example, it's not only delivered within the clinics and hospitals, but it's a lot broader. So there's this delicate interconnection between us and things like pathogen, for example, and other organisms as part of this broad ecosystem. So I wanted to take this as a bit of an opportunity to create awareness of this concept, One Health, and then the connection that we have and how we impact them and them on us. So a bit of a disclaimer, I have to do this, unfortunately. I'm not going to read this out loud. It's essentially that the view I express here is my own, and then they do not necessarily represent the opinions of the organizations I work for or the partners. A little bit about me. So I currently work as a head of product at the Center for Infectious Disease, Genomics and One Health. So we're about 25 people. We're comprised of microbiologists, software engineers, bioinformaticians, and IT professional myself. So prior to my role, I was working as a director in health informatics at Providence Healthcare. So I primarily work in healthcare sector. So it's been doing analytics and IT work in the last 20 years or so. In addition to my current role, I'm the mom of 2 teenagers and researchers and also a cancer patient advocate. So you see the picture of me at BC Cancer, that was last year. I was diagnosed with stage 3 cancer and then receiving chemo, radiations, and the whole slew. On the bottom, you see me exactly a year later, this July, in Australia. So I was speaking at a conference and decided to do a little bit of detour and a surf in Sydney, among other places. So this is me on Manly Beach and surfing. So this is slightly before I started surfing. Very interesting sport. I'm not the expert for it, but yeah, so it was a bit of a journey last year for me personally. So for those of you who are at the keynote by Andrew, he spoke about the resilience, right? Ability to bounce back from disaster. So that certainly resonated with me for sure. If you'd like to know more about some of the advocacy work that I do with Ministry of Health and Colorectal Cancer Canada, then come see me afterwards. I love to talk more. For me, the lesson learned from last year was that my research became my advocacy, and my advocacy became part of my research. So the research that I do, the work I do within my organization is an opportunity for me to contribute to my own community. As you imagine that the pandemic, I was diagnosed during the pandemic as a cancer patient, and cancer patient community was one of the hardest hit as an immune compromised group of people. So it was a very hard time for a lot of us during the pandemic. And I happened to be doing pathogen genomics as part of my research and part of my work. So I see those personal and professional, the passions got merged and aligned throughout my cancer journey. Like to acknowledge a lot of organizations we closely work with. So pathogen genomic is not a local use case. It's pretty global, as you have seen during the pandemic. So we work very closely with the regional authorities, such as Fraser Health and Providence Healthcare, as well as the national authority, Public Health Agency of Canada, and the globally organizations such as LCHS7, which is the healthcare data standard organizations that most EHR systems adopt to. So a lot of partnership, both at the global level, national, and then the local level that's happening. We currently are serving 2 major clients, Public Health Agency of Canada, as well as FDA in US, by working with them and then co-developing various tools used for various different kinds of infectious disease analysis. So UN Statistic Division, because that's one of my sort of strengths in terms of professional background. And then we're focusing on privacy element in terms of sharing some of this, the health data broadly at the local, regional, and then national level. So I like to bring back, I guess, a little bit of bad memory. I don't know about you, but every time I look at this picture, I get a little bit emotional. It reminds me of the fear that I had. If I get sick, will I be taken care of? I'm looking at overcrowded hospital here as a bit of a imagery. And what about my loved one? I mean, do we have space? So, I mean, to me, this really is a reminder of the fear and the anxiety that was happening to me at the time. Not all bad happened during the pandemic. I mean, this is the good news that I'm going to actually turn myself into in the next little while to talk about. So as during the COVID-19 pandemic, we have built huge amount of capacity. In fact, that it was the first pandemic, we were able to leverage pathogen genomics information extensively for various public health interventions. And then we're very successful, as you all know. And there, as part of that, it's not just the sequencing capacity we have built up. So things like the sequencing machine that generates DNA and RNA genomic information within the hospitals and healthcare organization, but also computing power, that the ability to process huge amount of data. All the public health organizations have invested heavily in that. So we're really looking at this like opportunity beyond COVID to leverage genomic information into our everyday life. So one of the work that the progress I'm really proud of, and then this is in partnership with the EOtec2023, which is the healthcare data standard organization, is that we like to create a data specification and standards around how pathogen genomic data can be used. So imagine yourself going into hospital and maybe 5-7 years, and then you caught some kind of bug or virus. They run the whole genome sequencing analysis to know exactly what it is and then what mutation and variant it is. And then they are able to map that information to prescribe you better medications and better treatment plan. And they can find out where you got them. Was it importation event? You caught it during your travel, or was it something, outbreak investigation or outbreak exposure that you've been locally exposed to? So imagine sort of that type of experience that you could have through data, pathogen genomic information being standardized within the hospital setting. So that's one of the work that myself is leading within the lab by working together with the global health organizations. So that's healthcare in terms of what's happening, and then leveraging and tapping into the existing capacity we have built up during SARS-CoV-2. And there's a lot more infectious diseases that we can get into in terms of broader use cases we like to pivot into in the next little while. Before I kind of switch gears into wastewater context, so unlike healthcare, I think there's more things to be figured out in the context of wastewater, for example. I mean, in healthcare, every hospital you visit, Vancouver, Coastal, Providence, they all have sequencing devices. They're in the early stage of building up that analytics pipeline. So I would say that the capacity is already there in terms of managing and then using pathogen genomic information. In wastewater context, outside of COVID-19, we're still fairly, I guess, premature in terms of being able to do that really well. So, and myself operating primarily in healthcare, this is also a learning opportunity to hear from you in terms of how and how exactly we can use pathogen genomic information in the wastewater context. And I'm going to talk a little bit about use case. The keynote Andrew talked about the use case, which was the water contamination due to plastic exposure. So this one is about the antimicrobial resistance bacteria that may be living in the sewage, and then how we can best monitor them. So just a little bit of background information before we jump into the use case. So genomic data is rich with information. So this was one of the visualization tool that was globally adopted. It's called NextTrain. So without getting into too much of a detail, on the left-hand side, you're looking at the lineage of a different variant. So on the very corner, you see that the Wuhan variant that first came out at the beginning of the pandemic. And then you see how that it sort of goes all the way to the yellow. There's a number of different variants that are expressed that made it come from some of these earlier variants. So genomic information give you this ability to create such phylogeny trees so you can better understand where things came from. And on the right, you see the global distribution of different variants. And then this is another advantage of genomic information to give you that more granular information about what type of variant and mutation, and then where that may have come from. This is our own labs product. We call it COVID MVP visualization tool. So in addition to the phylogeny information, this gives you even more granular information by being able to tap into genomic information. So on the left, again, you're looking at different kind of variant, Alpha, Omicron, and then there's actually subvariant within those. And on the x-axis, you're looking at the position on the chromosome. So what we're trying to do here is that across this variant, and then where are the mutations happening on what position,
And then having this information really help you understand that, hey, the mutations are happening on this particular chromosome, and then what are some of the function, which can then relate to severity and transmissibility of a particular pathogen. So Omicron, as you know, that it was, not as severe as earlier variant, but it had acquired ability to spread very rapidly. So in terms of phenotypic information, what's relevant for our direct health, severity and transmissibility are some of the things that we like to investigate and understand further. So switching back to wastewater, and to me, the wastewater represents huge opportunity. One, it's very, very new. So there isn't a lot of framework and standardized approach that are happening here. And wastewater can serve as an early warning tool. So for example, asymptomatic patient or any individual and got infected with the virus bacteria, and it gets released into, that flushed down the toilet and then into the sewage. Within the 3 to 5 days, you can collect that information and potentially understand what's happening there, even before that individual went to the hospital or clinic for testing. So sewage, the wastewater has such opportunity. So as one of the early warning, so, the people sitting in this room might actually get information even prior or before the hospital lab acquires such information with regards to, say, emergence of certain variant, for example. So there's a huge opportunity that, in my opinion, there's as using sewage or the wastewater as an early warning system as part of a broader public health. But it's also the area where there isn't a lot of standards and then the framework that's been built up to date. So a very interesting area. And as I say, I primarily operate in healthcare sector. So this is a learning experience for myself and our lab as well. And I'd like to invite you the feedback, and we'll have some Q&A at the end of this presentation to see what you guys think about the opportunities and current challenges. So in terms of wastewater, just a couple of examples of what type of information we could get from wastewater. First and foremost, species level information, which type of pathogen and taxonomy that are present in wastewater. And some organisms might die during the treatment process, some not. And I'll talk a little bit about sampling process later on, how scientists and then the folks that I work with within the lab, we have no idea how and then where the data is coming from. And then in some of the cases that we go through a very extensive Q&A process because the water might be too diluted, it doesn't have enough DNA content in it, and then have to send it back and then go through that iterations again. So to me, that it's really important that the people like scientists, bioinformaticians, we need to get out and really kind of work together with the people who are involved as part of sampling in the first place. So there needs to be that coordination that needs to be in place for something like genomic surveillance to work properly. So species level informations, evolution of species, how organisms mutate. So I just spoke about how the wastewater or sewage can be the birthplace for emerging pathogens or a new variant because they might be exposed to a low level of antibiotics in the sewage in the organisms who live there. So there's a lot there in terms of how organism may mutate and evolve within this very distinct, interesting environment. Third one is genotypic information. So I know a lot of standard tests might give you drug susceptibility, for example, as part of standardized phenotypic testing. So that's the typical testing that could be done in the hospital lab or any other lab per se. This genomic testing is somewhat unique. So I'm going to talk about different type of genomic testing. So whether it's using whole genome sequencing or focusing on a very targeted species out of isolates. But it does give you a lot more granular information about genotypes, so things like drug resistance genes. And then what are some of the mechanisms for them to transfer their drug resistance gene, whether it's plasmid mediated or through chromosome. So this is a very high level flow. And then there's a source at the bottom for those of you who like to go back and sort of see this through. And I'm going to use antimicrobial resistance bacteria as an example, specifically E. coli. And in terms of significance of AMR genes, antimicrobial resistance bacteria. WHO declared it as one of the most critical public health threat in 2019. So in 2019, there were about 1.3 million deaths related to antimicrobial resistance genes in healthcare collectively, globally. And as someone who used to work within the hospital here, I've seen it, the cases myself, where the patient carrying AMR genes, and then it can spread very quickly across surgical wards, for example. And then it's a very difficult challenge for the people who are recovering from surgery, particularly a surgical patient, inpatient within the hospital. So this is a critical issue, because the antibiotics that, for people who are recovering from infection, what are you going to do, right? So this is a very, very challenging the public health issue in terms of significance. So back to this flow. So say you have, can't really see the letters there, my apologies. So there's environmental bacteria potentially carrying resistance genes. So you're starting from the left corner there, and then it gets released into through the sewage or toilet, etc., into the wastewater stream. And then bacteria can be isolated from wastewater, say it's E. coli. And then there's two different broad approaches. So on this side, you're seeing more of a standardized approach. So typical phenotypic testing to characterize, hey, do we have a drug susceptibility? And then, what type of susceptibility are we looking at? So this gives you somewhat limited information on this side. On the right-hand side, if you like to acquire genomic information, so DNA, RNA, etc., right? And in the bacteria context, it's mostly DNA. So you extract those DNA information and then understand, and then being able to characterize broadly. So not only it can give you a very specific genotype, so which type of AMR gene, for example, and it also gives you the information around the mechanism of such transfer. So things like E. coli, Shigella, same thing, bacteria. So there's a concept called horizontal gene transfer. So once the bacteria acquire antimicrobial resistant genes, it can be transferred across species. So that's where this bacteria stuff is really interesting. The way that they can spread some of their genetic material is fundamentally different from how humans reproduce. So they can actually, spread this antimicrobial resistance gene across species through a concept called plasmid. But so it could be rapidly spread all across. And then obviously we're talking about organisms. They're living things. So they mutate as they live, and then they spread across species and within species. So talk more about antimicrobial resistance monitoring. So I mentioned that especially in the wastewater context, this is a very much emerging area that's coming up. And then therefore there's still lack of standards, and then, things like a quality control. And I think that one of the solutions might be that we need to just bring together, scientists, informaticians together with the, folks in this group who are involved with the downstream and upstream sampling. And I think that coordination is essential and necessary. Here, I'm just going to talk about the different type of method. qPCR, it's an application method. You guys probably heard about PCR and the COVID-19 context. It's a quantitative PCR. So there's a lot of similarity in terms of how your snot can be collected and then tested for COVID, different variant, and then this approach. There's this concept of culturing. So you have a specific species you like to target. So it refers to a method around growing bacteria in a lab. So that's culturing. Metagenomics is up and coming sort of cutting edge methodology in silico, like quantitative methods. So not only we're kind of targeting a very specific gene or target species, you can actually sequence and analyze, characterize as a group of species altogether. So it's up and coming methodology when it comes to further characterizing and analyzing genomic information. So there's a lot of different approaches, and then a lot of different ways to collect information and analyze the information. So how does one go about, do what? Where's the playbook and framework and standards? So it's very difficult for non-specialists to go into the space and then figure out, hey, we have this use case, so I'm going to use this. Because there's simply too many approaches and then too many things involved for each of the pipeline. So I said there's a lot involved. It's not, if you were to do a antimicrobial resistant monitoring and do some kind of analysis, it's not like, there's this a tool, just run it. I mean, it's a lot more complicated than that, which is why we need to really advocate for the standard and quality control for this to be operationalized and to scale up beyond just the ad hoc research type of project. So there's a lot involved, but it's not to say that it can't be done. I mean, I talked about the healthcare use cases. It's a whole more complicated in terms of how to organize the information and use it for clinical practices. And then they have done that. So in the healthcare community, myself is working on the pathogen genomic specification to be used as part of the EHR system. That's our electronic healthcare system that most of EHR vendors adopt to. So it's complicated, but it's very possible. And then healthcare is definitely leading it. So if you were to think about, hey, what does a standard framework and a standardized approach look like if you were to apply genomic information in wastewater context? So this is one of many frameworks that's been proposed to date. And I'll just go through some of these. So it really depends on what tools and what type of sampling you like to do. It depends on your use case, what you like to address. So what is the objective of your AMI monitoring program? Say, antimicrobial resistance, it's a significant public health threat, and then we like to be better monitoring it as part of wastewater. You might want to assess AMR status in a human population. In that case, you like to sample from influent sewage. You like to simply identify drug resistance gene escaping from water treatment plants. Then you want to do a different type of sampling. Here, you want to look at the sewage overflow and then wastewater effluent. And then you might want to use an analytics technique to culture AMR and pathogen and go through the whole genome sequencing or AMI profiling. So you see that depending on the question you like to address, the way you need to sample and which analytic processes and then the sequencing processes, they'll all be different. Quality removal rate. So how much of a pathogen are you really removing from this wastewater treatment process? And if you want to do that, you want to look at the recycled water and then influent effluent, and you might want to consider techniques such as qPCR. And you might want to look at the metagenomics for further characterization. So again, it's the case depending on the question you have. You might want to sample differently, and as well as looking at different type of sequencing approaches, as well as analytical approaches. And same thing, assess potential for a drug resistance to evolve. So I mentioned that the sewage it's the birthplace for emerging pathogens when it comes to, or variant when it comes to antimicrobial resistant bacteria, because the organisms who live there are exposed to the low dose of antibiotic constantly. So it's this unique birthplace for various the emerging variants of organism can happen. So if you like to monitor for that, then what are some of the approaches and how do you go about sampling that? So this is one proposal, and then there's that I know that there has been wide adoption of this particular tool or another. As I mentioned many times, this is still emerging area. The standards and the QA process in particular, there's still a lot to be fleshed out. I talk about sampling as part of the proposed framework. So there's a lot there in terms of a sampling strategy. So I got this map from Kopna. This is a map of sewage and drainage services in Metro Vancouver, which I know nothing about. It seems to indicate that there's some kind of overflow that's happening in a real-time basis. So you can kind of see, where the overflow is happening, and then which can be incorporated as part of the broader sampling technology when monitoring for things like antimicrobial resistance gene. This is just an example to get you to think about, and then get you to recognize the importance of how people need to work together. So people who may be sampling, and then understanding the intricacy of different network, and then how things move. And then those people need to work together, obviously, with bioinformaticians and the people who are actually doing the sequencing as well as the analysis. So privacy is important to me. I work as part of the UN's Privacy Enhancing Technology Lab, and privacy being as one of the fundamental human right. We've seen a lot of fierce debate during the COVID pandemic that data sharing in particular. There's a public good, and then there's an individual privacy, and then the trade-off between that. So, and as you've seen, that technology is such that, or the technology landscape that we live in, is such that there's always re-identification risk and therefore individual harm associated with data sharing. Yet data sharing is so critical. I mean, that's how we actually, dealt with the COVID-19 pandemic, by data sharing and, which pathogens and which variants is occurring anywhere. But there's always that risk, and then there's that patient or individuals at the end of that line who may be adversely affected by data sharing. So privacy is something I feel that we all need to be responsible for people who are handling sample, to the people who are actually doing the analysis, to ensure that there's no individual harm as part of what you're doing. And then, whether you're doing the analysis or doing the sampling. Um, there's a really nice, interesting article about the wastewater surveillance potentially carrying privacy concern. It was titled as the poop doesn't lie. A pretty catchy title. And I agree. There's a huge benefit of sharing data. So say in 3 to 5 years, this genomic surveillance has been operationalized fully using wastewater. And then you have a possibility to zero in on a smaller area. Or maybe using the data, there's a possibility to stigmatize a certain population, which is very much happening right now with the Shigella outbreak that's happening in downtown East Vancouver for a homeless population. So there's a number of privacy harm that we can that could happen as part of this data sharing and genomics operation, even in wastewater. So this is not to say that don't share data. We absolutely need to. But we have to kind of look at the standardization of data, and then recognizing that coordination between local, regional, and national global authority are critical. But as for all of us, the privacy is important, and then there needs to be a recognition, and then understanding the need for safeguarding against individual harm. There's a bunch of different safeguarding and then techniques and tools and processes you can use in terms of preserving privacy. But I'm not going to get into all that detail, but rather I'm just going to leave it at that privacy is very important. And then when it comes to data sharing of genomic information and sample information, there's always that re-identification risk, even if the data is anonymized. So that's it for my presentation. And like I said, I'm learning as I go, and especially in the wastewater and the sewage context. So I like to invite you to sort of provide feedback, and I'm really curious about what you guys think about this, upcoming new approaches around genomic surveillance in wastewater. Thank you very much for your time.
Off the top of my head, me and him work on a lift station. We had challenges with our solids being broken down, and then what we identified in my village says a lot of elders, they had antibiotics and stuff like that, kill a lot of bugs in our anaerobic system. So would that be challenging for this kind of testing?
On here. Thanks for the question. Are you talking specifically about testing done in wastewater context or in general?
I'm not a doctor or anything, so what I got, you wanted to possibly test effluent or we had an issue with solids being broken down, and it's because I had a lot of elders in my village, and they're on whatever medication for cancer, everything else. So, and it really did a number on my system, and then we had to figure out a way to get the bugs restarted again. I just helped with us breaking down the solids. So, with all your testing and everything else, so would that be an issue trying to target certain pathogens?
Absolutely. The data quality and I talked about lack of QC, that's always an issue, because as a group of lab people, like informaticians, that we get the sample and often what we see is that maybe there isn't enough DNA content in there. So we have to kind of send it back and ask for questions. So the wastewater, especially in the original format, it's often sometimes too diluted. So there's a process that's actually called for in terms of condensing it and then before the extraction of DNA. So, and then in terms of how, one were to figure out, it really depends on the sample and then what type of genetic content you have in the original sample that triggers what type of downstream further QA analysis and then the analysis that's possible. So, I mean, your question is really an open question. And then typically right now, how it's done is that it's done through trial and error. There isn't any sort of framework to deal with antimicrobial resistance monitoring, specifically in a remote community.
Well, actually, I've heard.
Oh, okay.
I know.
It's a good question. I'd love to follow up in terms of what sampling is currently done, because to my knowledge that there isn't any routine surveillance of antimicrobial resistance. So it sounds like this was a separate project that you've been involved with, or? Yeah. Yeah, absolutely. In that case, I would look at if, say, there isn't a lot of genetic material to begin with, and typically what I've seen is that not only you kind of try to do qPCR or the culturing technique, so metagenomics is another technique that could potentially be applied, in addition to those the traditional approaches. But I can't really say for sure without really understanding the details of the project. But I'd love to chat more if you're willing to kind of share some of your use cases. Thank you for your question. Thank you very much.
Wanted to say a round of applause, so please and thank you. We've got our next session starting at 11:15, I believe. So we got a bit of time and we'll be back at 11:15. Thank you.